relevant to what I learned there. Where we're going to focus in this next part is more so on the theory and electronic structure of solids. Why are we going to that point? Well, if you flip back to the pictures that you have of where we started talking about electron density maps, you can see the electron density maps give us a good idea of where the nuclei are, but they don't tell us like true atomic positions. A lot of times we have to use molecular modeling to figure out what do those systems look like, and a lot of times with the protons. So we're going to have to look at molecular models of solids, and if we want to understand the molecular orbitals that are, or the electronic structure of solids, we need to discuss theory. Okay, so really small particles, what type of physics do they follow? Yeah, they follow quantum physics. Okay, so we're going to talk a lot about quantum mechanics. Classical physics is a lie, but it's an okay approximation for big stuff. And I'm going to use big, depending on what frame you look at, how big. Okay, fine. Inherently, what's the difference between classical or Newtonian physics and quantum physics? It has to do with that word quantum. What does quantum mean? Quantized. It's quantized. Yep. Physics is quantized. I'm going to put the tiny, and I'm going to put it in quotes because depending on who you are, it might not be so tiny. What does that word quantized mean? Yep. Specific, discrete values. And that's really weird, right? Like, okay, guess how much I weigh? 180? Whoa! Apparently I gained a lot of weight on my trip. Lily, how much do I weigh? That's okay, just guess. Do it, quick, hurry.
145.
145, Joe says. A good number, we got 2 for 145. 150. I'm 155. I weighed myself this morning. Okay, pounds. Man, my gym gains must be looking great. But anyway, all right. So in a quantized world, let's say I'm a quantum system and I have a quantum muffin sitting in front of me. The weights that you guys guessed are the only allotted specific quantized values of my weight that I could have. So I weigh 155, I eat a muffin. What's my weight gonna go to? Boom, jumps right to 180. There is no slowly working my way up. Immediately, bam, obese BMI. There we go. I'm there. Now I go to the bathroom. Bam, I drop back down to 155. I go to the bathroom again. The muffin did not sit well with me. I would jump to that and I'd keep going down. And there would be nothing in between. Quantization is really weird, but it happens. Especially for small things. Okay, so that's kind of the idea behind quantum mechanics. We got to go there, but we have to have mathematics in models to describe what we're seeing. Does anybody know what is the current best model that we can use to describe wave function? Schrodinger's equation is one of the better ones that we can utilize. So we're going to talk about the Schrodinger equation. Yep. Well, we're going to get there. Erwin Schrodinger, he won the Nobel Prize. I know Lily knows this. I don't know if you guys know it. He developed one of the most fundamental equations, which he absolutely hated. He did not like it at all. He thought it was completely absurd, but it kept working. They did not want to give him the Nobel Prize, though, based upon his lifestyle. Does anybody know why they did not want to give him the Nobel Prize?
Gross and probably shut it in.
Nope. What was it? He wasn't a. Oh, I mean, at that time, we say he came from Vienna, like a lot of the other people. He was not a Nazi, though. He was actually anti-Nazi, very much so. The Nazis wanted him gone, like with a lot of the people. He was not Jewish, though. That's not why they wanted to get rid of him, but it's based upon his lifestyle. You can answer if you want. Yeah.
Because he had like, if he had some like interesting lifestyle things going on, did he have like multiple wives?
He had a wife and a couple of mistresses, and his wife was also sleeping with other people, and they were all okay with it. What was that? Yeah. Oh yeah. Yeah. He was a polygamist. Well, except no, you want to get married in that situation, right? I don't know. But he wanted to live that kind of lifestyle. Many universities would not accept him, but the University of Dublin did, and that's where he moved from Vienna to Dublin. That's why he ended up there. Okay, yeah, exactly. Have you ever seen a picture of Erwin Schrodinger, though? Man, it makes me feel good about myself. Yeah, that's the kind of game you can play. He developed this equation, and it's one of the most beautiful equations that you can find. It looks insanely simple. It is not, but we'll talk about what these are in a second. This contains all of chemistry and most of physics in here, which is amazing. Really, that's why we have computers crunching. When I was a student, quantum mechanics was really an academic exercise, and it's growing. It's growing incredibly fast because you can see the potential of just plugging stuff in. We would be doing that if it worked perfectly. There's other issues with it, which we'll talk about. But if it worked perfectly, none of you guys would be in the lab ever. You'd just be doing this all the time because it would give you the correct answer. All right, now, Joe, you want to jump ahead. You really want to know what these things are. Let's talk about what these things are. Does anybody know what any of these symbols mean or are? Yeah, go for one. This is a Hamiltonian operator. Okay, this is a Hamiltonian operator. Any other ones?
Does E stand for some kind of energy?
E is for energy.
Boom.
Yes. These are wave functions. Okay. Energy, of course, is important. If we know the energy of the system, we can derive pretty much anything like chemical potential, where chemical potential is huge. That you can use that from thermodynamics to predict anything you want of a system. It mixing with other stuff, it's great. The wave function is kind of a weird thing, though. Does anybody have a working definition or can throw up some words associated with what is a wave function? It doesn't necessarily have to be. What's that? We're gonna do integrals related to it. There are imaginary numbers in it a lot of times. What's it describing? Yeah. Yep. So what it is it's a mathematical function that's used to describe the wave-like behavior of electrons. We're going to write that down, and we're going to translate that into real people speak in a minute. Function to describe wave-like behavior. Electron, whether that electron be existing in space, it's wrapped up in an atom or a molecule. Okay. Wave functions are just a model. They're not observable. We've never measured one. By the nature of them, you can't measure them. They could not be real at all, but they just describe the system very well. Okay. Other aspects to this. Does anybody know what type of equation this is called? It is related to differential equations. Just this whole thing. So we have a Hamiltonian that operates on a function. It spits out a scalar, gives us that same function back. Yep, it's an eigenfunction.
Oh no.
Yep.
No.
You've taken linear equations or linear algebra? Okay. So you operate, that's fine because it's better. You operate on a function, resulting in a scalar times that function. And it's got to be the same function out. Okay, so we're going to utilize this a little bit. We're just going to do a quick example where I'm going to give you a wave function. We're going to evaluate it and we get an energy out. Okay? We're then going to take this further to go to what is the Hamiltonian operator and how does it look for molecules, and then eventually we'll get to solids. Okay? Am I okay to erase this side? That is currently true, but there's ways to make approximations to get around it, and there are other methods you can use to do better. They're just tough. Okay, example. Given h bar for a 1D particle in a box. Yeah. Mine too. Is negative h bar squared over 2m. Okay. Before we go further, are you guys familiar with these symbols? Anybody not know what the symbol means? Joe, this is just the same thing as a derivative sign. It's a partial derivative. Have you seen partial derivatives yet or no?
No, I have not.
Okay. Okay, that's fine that you know what they look like. You can think about these as just big D, but it's so you only take a differential with respect to x if you have multiple variables in it. Okay? That's the short and dirty. Yeah. Actually, it's usually nice because it makes everything better. The wave function, or easier to evaluate, is we have psi of x is equal to square root 2 over a sine n pi x over a. Okay. For the energy. Okay. What are we looking for in this problem? Yep. Just expression for the energy. What information are we going to need? All h bar, or excuse me, h hat. Have I been saying h bar?
Yes.
Oh, that's terrible. This is h bar. H hat. H bar is Planck's constant divided by 2 pi. It just shows up a bunch, so they give it a new symbol, h bar. And then eventually we just make that 1.
H bar, is that just their way of converting it into radiant?
No. There's something, it just shows up.
It's just annoying.
So you don't have fractions on that.
Under that, it says the possibility of Under.
No, that's a 2.
Yep.
It's 2.
That's a 2. That's not a partial.
Okay, to be fair.
I know, it looks bad. I am so sorry.
Twos, Q's, and
Yeah, and my handwriting's absolute garbage, so that's got to be great too. Okay, so we got to find the energy. We're given these two things. How are we going to figure out the energy?
Is that M or N? Sorry, just
This right here?
no, negative h bar squared over, is it 2m?
2m, yep.
Okay.
Man, even worse. There we go.
That's okay, I'm the same way.
Okay, how we find an energy?
we're gonna have a Hamiltonian, and then we're gonna,
Yeah.
well,
What's it got to operate on?
It's operate on the wave function and the non-constant.
Yes, that's what we should get out. So we need to get that same function back out. So we're going to apply our Hamiltonian, which is just this. To okay. How do you suggest to go forward with this thing?
Partial,
Mhm.
second partial.
Yep, so we'll do the first one. Can we pull anything out to make our lives easier?
Yeah, well, we can get square root 2.
Yeah, that's what I would do. Pull out that square root 2 over a. Then we got to take the derivative. So we're going to leave first derivative alone. If I take a derivative of sine n pi x over a, what am I going to get?
We're going to get n pi over a cosine of n pi x.
Yep. Okay. Now what could we do with that? Yep. I'm going to pull out the n pi over a. You might be asking, why not just combine these things? There's a reason. We'll see in a second. Okay, take a derivative of cosine n pi x over a. Okay, combine some stuff together. What else?
Oh, well, then you have sine n pi x over a.
Yep. Okay. What does this tell us? Okay, where is E? Yeah. This thing
Oh, that looks familiar.
is E. I know I had your calculus professor. If you took calculus here, I give them examples to feed,
Oh, yeah.
and they use them, and it helps me so much.
He said that's down this pipeline before.
So as you're cursing your math professors out, me and Dr. Pianka are the real reasons you hate them.
Oh, no,
Sorry. What's this thing? Yep. So then, what's our energy expression?
Where's the negative?
It went away because
Yep.
Oh, got it.
Because there's a negative there. What's this going to get us? Yep. Okay, where we put a little e sub n there because we can change that quantum number. That's something for another class, though. Yep. You get the abuse later with me. You're taking modern right now. Oh, you're taking quantum. Oh, you'll get that. You've already dealt with that then, probably by this point, right? What are you guys at in quantum right now? Finite potentials?
We're solving a bunch of different operators.
Okay.
The plus one, minus one.
Oh, up and down. Yeah, I hated that one too. I like to go with practical quantum mechanics, which sounds like the biggest oxymoron on the planet. I saw your snicker, Lily. It was pretty good.
Doesn't that set you up to do quantum later then?
You can. There are other ways you can get around it.
Sounds like
Mhm.
Last time you disappeared, we did quantum harmonic oscillator.
Yeah. Yep, it's terrible. But yeah, you can use up and downs.
Easier to do in terms of Latin operators.
I agree.
You know what y'all are talking about. I'm gonna be. You're going to. You were speaking a whole different
No,
language.
I'm not sure, Jen.